continuing our discussion of section 3.10, and the first video was about linear approximations, and now we want to talk about differentials a little bit. But before we do, I just wanted to remind you what we looked at last time, and that was we had a function square root of x plus 6. We approximated it at x equals 3. By the way, you always have to have a point at which you're doing your approximation, or you're basing your approximation. So in this case, we're basing the approximation at x equals 3. And so then we came up with our tangent line approximation, L of x. Okay. Now before we go continue, I just wanted to make a couple of notes. Note 1, mathematicians like to use delta to stand for represents a change. Okay, so if you see like a delta x for example would mean a change in x, and then delta y is a change in y. Or for example, delta a would be a change in a, whatever a is. Okay, so whatever the delta is, right, I can get that rid of that. The delta something is a change in that something. Okay, so if x changes from x to x plus delta x, then x being the independent variable, right, that's going to induce a change in y. This induces a change in y, right, and so that change in y is going to be the change in your function values, right? Good. So whenever you see delta y, you can think that it's the actual change in y. Delta y is an actual change in your function given that x changes by delta x. Good. Alright. So delta y is a quantity that we can actually compute, and so is delta x. Alright. So in terms of our last example, x changed from 3 to 3.5, so delta x is equal to 0.5 in that case. What was the change in y? Well, the change in y is the square root of 9.5 minus the square root of 9, right? And I think we found, let me scroll up here to where we did it. Yeah, the square root of 9.5 was 3.082207, right? And so then we subtract 3 from that, so that's going to be about 3.0822 something minus 3, and so the actual change in y is that 0.0822. Good. Alright, so now we're ready to define a different change, and that is the differential. So differentials. Let me see if I can spell that a little better. So differentials. Okay, so if y is equal to f of x, then our Leibniz notation, we say that the derivative dy over dx is f prime of x. Well, the way Leibniz thought about the derivative, these things here, dy and dx, are actual little numbers, and so the dy over dx is an actual fraction. And so if we write dy equals f prime of x dx, these quantities right here, the d's, are called differentials. Okay, and so the differentials then are the little quantities here. We think of this as an approximated value of the derivative. So instead of taking the one way to think about it, right, is that dy over dx is actually the limit as the change in x goes to 0, right? And so your actual change in x is actually 0, but we're going to think of the change in x as a very small quantity. And if we do that, then the change in y should also be some small quantity. And in fact, from this equation, we see the relationship between the dy and the dx. So maybe we should have a quick example of that. Example. Suppose that f of x equals x minus 1 over x plus 1. Oops. Let me make sure I'm doing the right example. X plus 1 over x minus 1. Okay. And we'll go ahead and say that dx is equal to 1/10. Find dy at x equals 2. Okay, so the solution is that dy is equal to f prime of x times dx. And so when we take our derivative, f prime of x, we're going to need to use the quotient rule. So the derivative of the top function is 1 times the bottom function, which is x minus 1, minus the top function times the derivative of the bottom function, all divided by the bottom function squared. So if we simplify that, what do we get? Let's see, x minus 1 minus x minus 1. X's cancel, we get minus 2 divided by x minus 1 squared. Okay, and so what we're saying then is that dy in general is minus 2 over x minus 1 squared times dx. So now if x equals 2 and dx equals 1/10, we can compute dy, right? So dy in that case would be minus 2 over 2 minus 1 squared times 1/10. Good. Let's see, that's a 1 in the denominator, so that's minus 2/10 or minus 1/5. Good. So if dx is 1/10, right, then dy is negative 1/5. And so because our dy is negative, right, that means the function is going down. Good. All right. Now, how does dx, dy, delta x, and delta y all come together? Is there a relationship between those four things? So let y equal f of x, and x changes from x to x plus delta x. Right, so x has a change in x. So let's go ahead and draw a picture of a function starting at a point x and moving to x plus delta x, right, so that the change in x is down here on the x-axis. And now let's see, can we draw the delta y? Well, the f plus delta x is up here, right? So that's f of x plus delta x. And then down here is f of x. And so maybe I can draw it over here. This quantity then is the change in y, right? That's an actual change in y of the function from one point to the next. Okay. Now suppose I draw my tangent line to the function, right? And I have the same change in x. X goes from x to x plus delta x. Then if I use the function as an approximation to my line, or to my function, did I say that right? Use the line as an approximation to your function. It's getting late, sorry. Then the line has a change as well, right? This is the this is the top of the line, that's L of x plus delta x. And then f of x is equal to L of x, right? And so this bigger quantity from here to here is the change in the line, right? Change in the tangent line. And as we're going to see, this is actually equal to dy. Okay, and so we could probably see that, right? So how do you define the slope of a line here? I'm just taking this as this triangle right here. I'm just rewriting it over here. So this is my line here, right? And so the slope right at this point, this is f prime of x, that's the slope. That's equal to rise over run, right? And so if the run is delta x, then the rise is going to be f prime of x delta x, right? And do you recognize that that is, if we let delta x be equal to dx, which is normal, delta x equals dx, then this is f prime of x dx, and that is dy, sorry. So then geometrically then, the change in the line is dy, the change in the function is delta y. Change in line is dy, change in the function is delta y. Okay, and so again, remember dy can be computed as f prime of x dx, and that's the same thing as we always let dx be equal to delta x in our examples, while, oops, sorry about that, something went flying, the delta y is f of x plus delta x minus f of x. Okay, and so finally, I just want to say one thing. We typically we use dy to approximate the delta y. Okay, so we use dy, which is f prime of x dx, as an approximation to delta y. Okay, and we're going to see this in the next example, but we're running out of time, so I'll stop there. Hopefully all this notation hasn't messed with you too much. We've seen the graph before, we just never have given these numbers before. And so again, the change in y is going to be the change in the function. The dy is the change in the line as we go from x to x plus delta x. Okay, so in the next video we'll just work through some examples.